Good evening, doctors and assistants. We're so happy to welcome you out tonight to introduce you to Dr. David B. Harrell, double PhD, and he started off in molecular biology, headed to epidemiology, but in the meantime, in his study and journeys, and hopefully you've had a chance to look over his bibliography, it is 18 pages long. So he and Dr. Harris are ridiculous to talk to. Sometimes you have to stop and have them define what they just said. It's a word we never knew existed before. But their passion for what they do is what's led them into regenerative medicine, to the biological allografts, to quote-unquote stem cell type reaction treatment. And Dr. Harrell is going to give us some insights here that is going to really help clarify what is a stem cell, what are biological allografts, why would you want to do it. Now, it's really interesting. Doug Grant is the owner of OHS, Optimal Health System, who sponsors these along with myself and Clark Tilley. He was in a wheelchair and was introduced to chiropractic while in the wheelchair and has been able to walk and perform, and he's an athletic trainer. Most of you know him. My introduction to chiropractic when I was 20 years old was I was basically in a wheelchair. I was paralyzed from the waist down and in spasm from the waist up and in chronic pain. I walked into the chiropractor's office. No, I didn't walk in. They carried me in, literally, and I walked out. And that was my introduction to chiropractic and to my whole role now in the field that we're in. Now, Dr. Harrell, I'm going to have him define it just a little bit better. But between his PhDs, he was struck by lightning and wound up in a wheelchair for, I believe he told me, a decade. So, Dr. Harrell, let's just start right there with you, your personal journey, why you're doing what you're doing here, and enlighten us. And we'll maybe ask questions as we go, and maybe you can tell everybody how they can ask a question for as we go along.
Sure. So thank you very much for that fine introduction, and hello to everybody that's in attendance. As Dr. Brimhall mentioned, the lightning strike had me in a wheelchair for a decade, and getting out of the chair, what was interesting was I got to focus on work that I had done whilst a graduate student in molecular biology, with a little bit of focus on stem cells. And in this tissue regeneration pathway, the focus of how I got out of the wheelchair was to focus upon neurons. So historically, we thought neurons did not regenerate. That was Kajarin's harsh principle, no new neurons. That was dogma in the field. And we now know that that's untrue. So that's what led me down this pathway, was the fact that focus on tissue regeneration and the regeneration of neurons, nerves controlling muscle, is how I got out of the chair and walking again. That's pretty life impacting, and makes one want to focus on that as a field of study. Now, just as a reminder, those in attendance, you should have a drop-down box that says questions. In that drop-down box, you're allowed to type those questions. I will be reviewing those questions yes, at the end of the presentation, and then we'll walk through those. So please feel free to ask questions. I'll get through them as time allows. And so today, what I really want to focus on, you saw this title of, is it a stem cell treatment or regenerative medicine? How do all those things sort of come into play? So we're going to talk about that. I want to give you this, conflict of interest statement. I have nothing that is in direct conflict of interest for this presentation. For me, when I look at research or I look at hard work, and we're going to have to do some really hard work today, because as clinicians, not everybody as a clinician is as enamored in basic science as basic scientists. So I understand that it might be a difficult beginning, and I liken that to climbing the mountain on a bicycle. And as you can see, I do a lot of cycling, both road and on the track in the velodrome. So we do all this tons of hard work so that we can fly downhill. And what I'm going to say is we're going to go through a discussion of some of the basic science of tissue regeneration, so that you can then think about it in your practice and why these why these tools in the practice of regenerative medicine will make sense. So fly fast, but we got to climb hard. I also like humor, and Chris Madden is one of my favorite cartoonists. I do have permission to use this image from him, but I would certainly encourage anybody who's interested in sort of science humor and scientific cartooning to visit Chris Madden's site. But here we have this scenario set before us where there's a job interview happening, and of course what's being presented is a Horseshack test. Only the conversation is not, you know, what do you see here, but rather, if you see anything, you can't be a scientist, because scientists cannot be impressionable and they must be objective. So we, even though I'm a PhD, and it pains me to say that not everything that happens in the laboratory happens in vivo, I can also say I like to laugh at myself, and sometimes scientists have to be a little bit impressionable. Okay, now the very least favorite thing to discuss is regulatory and the regulatory environment. The Food and Drug Administration has two groups that look at tools that get used in the regenerative medicine space, and one of those groups is CBER, the Center for Biologics Evaluation and Research. The other one is a device focus, but CBER is really the group you need to look at. And they have these rules on products they consider human, cell, tissue, and cellular and tissue-based products. So there's a comprehensive regulatory program under 21 CFR 1271. So that then gets broken down to various different product types, some that require massive amounts of study, just like a pharmaceutical, others that don't require pre-market approval, and people just go down a 510K pathway. So there are significant variations that are within the HCTPs. Now, I also want to give two really exciting things that just happened in the field of regenerative medicine. One of them is the state of Arkansas. Arkansas in March, I believe it was, passed the Emerging Therapies Act of 2017. So the state of Arkansas has said regenerative medicine is such a huge, important focus that for those who need to go arthroscopic surgery, instead of the surgery, the state will pay the fees for all state employees and teachers to avoid the surgery and have regenerative medicine. They are covering 100% of the costs and still anticipating $100 million savings in just a 6-month window. So we have, yes, the FDA to wrestle with, but we also have states jumping on this bandwagon and supporting it. And Texas has increased its ability for physicians in the state of Texas to do investigational stem cell therapies and treatments to patients with chronic disease of terminal illness. And this is one of the reasons I think it's really important to have a very clear definition as to what a stem cell is. A physician in Texas phoned me and said, my hospital is stopping me from using, you know, what should be called a biologic allograft, because they had that surgeon had marketed it as stem cell therapy. And Texas said, you know, we just passed this thing for stem cell therapy, and it's only limited to these people, and or a large academic institution. So people are calling things stem cell treatments that actually are not stem cell treatments. Scientifically, a stem cell treatment is a treatment that involves stem cells only. That's also how the FDA interprets it. That's also how a very larger, more powerful body interprets it, and that's called the FTC, which the DOJ is part of. So, you know, there are big things, and we need to really look at what terms we use. So I'm going to skip this slide. Now, what's interesting, Andre Guide said, look, you don't discover new land without consenting to lose sight of shore for a very long time. And where we're going today is on this journey to see new land, right? So you're going to have to get a little bit uncomfortable and remember a little bit of your basic science and freshman chemistry and freshman biology and maybe even freshman physics to get through today. But once we do, you're going to see a whole new land, and it should be very exciting. So we're going to talk about the definition of stem cells and tissue regeneration and break down the various kinds of cells and what cell cycles are like and things like this. All right, so let's look at the definition of a stem cell. Ernst Haeckel, who's a German biologist in the 19th century, first used the term Stammzelle, right? So the English would be, translation of that is stem cell. And what he meant initially was that this stem cell was a unicellular organism from which multicellular organisms sprang. So it was the ancestor cell. He then used the term very differently, and the word stem cell came to mean a fertilized egg, which becomes an organism, right? And so that's actually a very, very interesting change. In 1869, so we're still 19th century here, and we're talking about stem cells, right? So E.B. Wilson at Columbia was the first one to use the word stem cells in English. And he said these are special cells that can give rise to specialized cells. So that's very similar to how we use the term stem cell today. And then the very first stem cell study published was in 1907 with Ross Granville Harrison, who was at Johns Hopkins and then at Yale. And they focused on neuroblast differentiation. So all of this Kajaran's harsh principle, the very first stem cell we find has to do with an adult neural stem cell, which is really quite amazing. So the word stem cell is not new. Regenerative medicine is not new, as we're going to look at. So how do we define a stem cell today? Well, there are many kinds of stem cells, number one. But a stem cell is defined, it's characterized as a cell that's capable of both self-renewal, so it can form a clonogenic entity. It makes an exact picture of itself, and it has the capability of what's called asymmetric division. So it can make exactly itself, or it makes a different kind of cell. And what we're going to learn is these two things are super fascinating, and in injury, not all of the rules apply as they do in homeostasis. So there are different rules for injury versus homeostasis regarding even terminally differentiated cells, not just a stem cell. Now, the discussion of potency, so is it pluripotent? Is it a totipotent cell? Is it multipotent, or is it unipotent? It's very contentious to have that discussion, because there are people who say, well, a stem cell must be totipotent. It must be able to make every single cell of any of the organism, and that's how we define it. Well, those kind of cells are very special, and those are generally called embryonic stem cells. And then there's a way to make cells behave similar to that that we call an induced pluripotent stem cell. So it becomes embryonic-like. And it's taken from terminally differentiated cells. So we're going to talk about why that is such a big thing. But the idea of potency is left off the table, because we have skin stem cells. And those skin stem cells under homeostasis only make one thing, and that is skin. So we can't say that it has to be totipotent or multipotent. It can also be unipotent and still be a stem cell. Now, what's interesting, there's this whole, there's this idea of stem cells being quote unquote immortal. First of all, I have a significant problem with that term, because I don't know anybody that is immortal. How do you define immortality when we are mortals? How do we know that a cell never, ever, 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 ever dies? We don't. And in fact, guess what we do know is we're so bad at characterizing the environment that the cells natively live, we can't demonstrate extensive proliferation except for in two cells, one of those being a cell we thought didn't exist, the adult neural stem cell. So we need to learn better about self-renewal factors to be able to replicate things in vitro. Now, when we look at regenerative medicine, I said it's both old and new, and we're going to see a little bit more about that in a moment. But the ancient Greeks knew of regenerative medicine. And I say that because the very first reference to tissue regeneration that's written anywhere is in Hesiod's Theogony. So Hesiod writes on the creation of the gods and the cosmos in his Theogony. And if you remember the story of Prometheus, Prometheus is credited with sort of science and mathematics, and Prometheus brings fire to humankind. Zeus then punishes Prometheus because fire was supposed to be reserved for the gods. So Prometheus is chained to a rock for 30,000 years. And each day an eagle comes and feasts upon Prometheus's liver. The liver regenerates. And the eagle comes the next day and eats upon it. The model organ we have for organ regeneration is the liver. We have no clue how the ancient Greeks knew that the liver regenerates, but somehow they did. So that is an example of regenerative hypertrophy. Today, what we're focused on in our discussion are tissue regeneration. But what I want to draw out is, while regenerative medicine might sound new, while the term stem cell might sound new, it's actually, these things are pretty old, and some of them being 4,000 to 5,000 years old in concept. Now, what is really new is this idea of plasticity. And plasticity, if you remember, sort of is how much a cell can morph and change, right? So we used to think, oh, we need stem cells, and a stem cell, if we put it into this region, that cell's gonna somehow become part of this region of trauma, and it's gonna grow all this new tissue and everything will be great. Well, guess what? None of that worked, right? So we had to start looking at things in much more detail. Well, one of the things that happens when we look at cell plasticity, we find that cellular plasticity is not limited to just stem cells. So if you have a complete genome, the cell, any cell with a complete genome can become any cell of the organism for which it was isolated. Now that's really fascinating. And we see this in 1996 with Dolly the sheep, which was somatic cell nuclear transfer. And then we see as proof, so Dolly the sheep was sort of proof principle. And then as proof of this are these iPS cells, where we just simply change the environment of the cell and they behave differently. The next thing is that of cellular uncertainty. So think back now to freshman chemistry, and you have the Heisenberg uncertainty principle, which was, you know, if you try to study something, you're going to alter it, right? Well, that same thing happens to cells. Once you isolate, you've taken the cell out of its native environment, and you therefore impact what it's going to do. So we have cellular uncertainty. Then what really makes me excited is this idea of stochasticity. Now, stochasticity is a constrained randomness, right? So we live in an environment that is random, but it's not completely random, but it's also not all predetermined. It's somewhere in between these things, and that's called stochasticity. And this is what fascinates me and gets me super excited in the morning, is that we have an eruption of quantum mechanics and quantum activity at the cellular level. And that's just mind-boggling, right? So what it says is that a cell can randomly become various things. And what we're going to see in the next slide is we have to think of a whole new cell cycle. So instead of thinking of these 4 phases, or if you add 5 phases, being first G0, which is a quiescent phase of this cell in hibernation, And then we talk about G and S and G2 and M, blah, 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 that typical freshman biology cell cycle. Well, we can actually change the cell cycle and say there's two parts that actually we can categorize a cell. The first part, which we call A, is active just after G1 begins to just before G1 ends. Now, that is the stochastic part of the cell cycle. That is a cell that is completely impacted by its environment. Okay. Then once we get into DNA synthesis, guess what happens? Yes, we go into this predetermined or this determined phase, and the randomness is eliminated. So it's a fascinating departure, and we see that multiple cells can do all sorts of things, and that stochasticity exists. So as we looked at tissue regeneration, I already mentioned it's older than we think, but it's also much newer than we think. And what I mean by that is this, what looks like perhaps a tough diagram, but please bear with me as we talk through it. So if you look at this C here, right, you see this C, that stands for canonical differentiation. So we have this stem cell, which can make another stem cell, or it can make this progenitor or this progenitor. And then this progenitor goes down this line and it makes this terminally differentiated cell. And this progenitor down here goes down this line and it makes these terminally differentiated cells. Okay, that's called canonical differentiation. Then we have this D here. I like actually to use the letter R, but it stands for dedifferentiation or redifferentiation if you use an R. So here we have a progenitor cell that sort of moves backwards in time, becomes stem cell-like, and then switches lineages completely through this retrograde activity. That's called redifferentiation. Then we have this T, and I put an asterisk there for a very important reason, because it was incredibly hotly debated for the first decade of this century. And what was happening in the early 2000s was that embryonic stem cell research was being squashed in many ways, and this idea that a progenitor of an adult could automatically, it could directly go to another line seemed like it might ruin or halt embryonic stem cell research altogether, rather than looking at that these things can be complementary. It was seen as one is going to kill the other. And so it was super hotly debated, this idea of transdifferentiation. It is no longer debated. It is a well-known fact. Okay. Then we get cell-cell fusion that can happen. So you get a multinucleated cell, which then goes into post-fusion reduction. Or we get nuclear fusion. We get this very large nucleus, and then we get post-fusion reduction. So all of these things are called plasticity, right? Or lead to plasticity and potency. Well, what's interesting is for the overwhelming majority, everything that's not canonical differentiation tends to take place following injury. So in other words, we don't see a lot of transdifferentiation or redifferentiation without there being injury. It can happen, but it's not very common. Canonical differentiation seems to rule homeostasis. As I mentioned, that first decade was pretty fierce, but 25 peer-reviewed studies focused on the plasticity of adult stem cells. 24 of those 25 showed positive result, and again, the fear was embryonic stuff would be shot down. Now, when I say embryonic stem cell, I mean very much an embryonic stem cell, and an embryonic stem cell is only up to 7 days post fertilization of the egg. So you can't say that, you know, a stem cell from a child is an embryonic stem cell. It is not. It is an adult stem cell after 7 days post fertilization. So people also have that misconception. But adult stem cells can be plastic, and no longer is that questioned. However, the most referenced paper during this time period is the one paper that showed that showed no plasticity. That paper was then retracted and explained, and yet people still quoted it as demonstration that adult stem cells do not have plasticity. Now, we're going to also talk about cell activity and communication. I call this slide Crines and Punishments only because it's so important to remember these terms and concepts that that I wanted you to be able to have, you know, some sort of mnemonic or some sort of recall device. And of course, the book Crimes and Punishment sort of come to hand, because in many ways, crime has happened on how we think stem cells should have operated versus how they actually do. And so we have this right here, this first crine is called autocrine, and that is a cell that acts upon itself, right? Then we have juxtacrine and paracrine effects. And the paracrine effect is different than juxtacrine only in the sense that a juxtacrine effect requires cell A and cell B to be touching through a membrane-bound protein. Paracrine says cell A can impact cell C or D, but they have to be really close by. And then we have an endocrine effect, and these are hormones that sort of operate at this range, so it acts over very long distances. Now, the overwhelming majority of tissue regeneration occurs through juxtacrine paracrine effects. In fact, if you're lucky, except for the case of hematopoietic stem cell transplant following myoablation for leukemia, if you're lucky, except for that scenario, the autocrine effect is 0 to 1%. In other words, it's almost non-existent. Okay, everything is coming out of this juxtacrine paracrine effect, and that is a tremendous departure from what we used to think about stem cell activity. No longer is it the cell you transplant, but rather the cell you transplant impacts all the neighboring cells, so that all the neighboring cells move out of quiescence. Oh, remember that G1 phase? That's the phase that the environment dictates everything about the cell. So the cell moves out of quiescence from G0 to G1, and it says, I'm in this environment, and this environment is loaded with cells saying, I need to regenerate stuff. Guess what happens? The endogenous quiescent cells are the ones responsible for regenerating tissue, not the transplant. However, those quiescent endogenous cells require a high cell load and signal load in order to activate. So there's a little bit of a departure from clinical discussion, but I believe it's incredibly important so that we actually can build a solid foundation rather than having buildings that topple over. Now, in the discussion of stem cells, there's a cell that probably most people listening have heard of. One called, it was first coined the term by Arnie Kaplan in 1987, and it was called a mesenchymal stem cell, and it has the acronym of an MSC. And for years and years and years, everybody thought this is the only cell that matters, right? It's called a mesenchymal stem cell because in vitro, we could make this cell form the 3 germ layers of the mesenchyme. Guess what? That's an in vitro artifact. Not one demonstration of this happening in vivo, and yet since 1987, it has been the focus. And when I talked, and I first said that an MSC is not a stem cell, I thought the field was going to behead me, and I had a very long talk with Kaplan and others that were certainly thought leaders, and I was the young upstart that was creating some waves. I'm happy to say that since 2001, Dr. Kaplan has coined a new term, and he calls them a medicinal signaling cell, still keeping the MSC acronym, but now teaches very clearly that it is not a stem cell at all, right? So the vision of seeing these MSCs as precursors of everything else is incorrect. We've moved beyond that, and yet that concept is both autocrine and ancient, and yet it is the concept that most clinicians run to and cling to because they haven't been able to keep up with the basic science, and basic scientists aren't exactly always the most communicative when it comes to interaction with clinicians. So we have a lot to work on together. MSCs, there are these tests for how one might define an MSC, whatever term you're going to call that cell. It has to meet certain criteria. So the International Society for Cell Therapy put together a minimum set of criteria. So it had to be negative for hematopoietic markers and had to have various other expressions of clusters of differentiation. And in vitro had to differentiate into various things. However, even all of the morphological tests and cells that met the minimal criteria, and in fact, when we expand into just rather than 7 surface markers, we look at 22 or even 200 surface markers. We can't distinguish between an MSC and a fibroblast. That's a differentiated cell, right? We can't do it with these things alone, so we're kind of bad at studying these things. In 1987, what Kaplan did demonstrate was something very interesting, and that was it's been known for quite a long time that MSCs in the bone marrow diminish with age. Okay, so at 35 years, you would expect 1 in 250,000 nucleated cells of the bone marrow to be an MSC, but at age 80, it's 1 in 1.5 million nucleated cells of the marrow. A hematopoietic stem cell in the bone marrow is at 1 in 10,000 to 1 in 15,000 nucleated cells of the marrow, and guess what? That remains consistent for life. So Hernigo, who did a study on injections of bone marrow for non-unions, found that age had no impact. So in other words, everybody was saying we have to focus on this MSC, 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 MSC. Well, we know that MSCs diminish with age in bone marrow, and if you're treating patients just with bone marrow for their bony defect, age should have an absolute outcome because there's such drop, and age had no outcome. So it begs a massive question there. One is that a fibroblast-like colony-forming unit actually does not measure an MSC, even though many people seem to think it does. The other is that there are other cells involved in tissue regeneration other than MSCs. One of those being the longest studied stem cell, and that's a hematopoietic stem cell. So that's what E. Donald Thomas used in 1957 for bone marrow transplantation. And just like MSCs, HSCs are not a single entity either. What we typically say is that cells that are CD34 positive, so this cluster of differentiation, the surface protein, the surface marker, has to positively express 34. Okay, but not all cells that express 34 are hematopoietic stem cells. Some are progenitors, and there are data to suggest that there are hematopoietic stem cells that are CD34 negative. No matter what we do know is that the traditional marker of a hematopoietic stem cell is CD34 positive. So like MSCs, whatever you want to call them, these cells can move, they mobilize, they home to regions of trauma. And one of the big things that HSCs and MSCs do is MSCs establish the niche, they establish the environment for these HSCs, and HSCs initially were thought to just make blood. We now know they do everything an MSC can do and more. Okay, so what I'm going to show you here is video, and I thank Harvest for allowing me to show this. But here we have an injury created in a zebrafish wound. Okay, so we have this wound site. There's a chemokine that gets expressed called stromal-derived factor 1, or CXCL12, that gets expressed, and that draws cells out of marrow space through the peripheral blood to home to this site of trauma. So we're actually watching cells migrating to that trauma site in order to regenerate that tissue. So this mobilization and this migration happen naturally. The problem is there's very little engraftment, and oftentimes the homeostatic demand on patients as well as the trauma are insufficient to address the issue, right? So unless you can mobilize a high enough number of cells into the region, you don't treat that region. That region, there's a difference. So think about it like this. There's a difference between tendinosis and tendinitis. Tendinitis is acute. The minute it's chronic, it's tendinosis. Now, the osis part is not just inflammation. It's actually tissue destruction. And the only way to overcome osis is with dropping a high cell load in, or a lot of factors to draw additional cells to stimulate the cascade of events that regenerates tissue. So osis is what should be used rather than itis. What's interesting is you drop the cells in. It's not the cells that you inject into that spot or all the factors that lead to it, but it's rather them stimulating endogenous cells to regenerate the tissue. So what brings about the change between tissue destruction to cell proliferation and reconstruction and repair is restoration of the vasculature. Okay, if you think about it, a cell must be within half a micron of a vessel in order to survive in almost every setting of the human body. Half a micron is not a lot of distance. It's got to be really close. So we need the restoration of the vasculature. So when you think about a broken bone, right, what's one of the first things that happens is you get the clot formation, you get inflammation, which draws additional cells, and what happens first is you get restoration of the vasculature so that the bone can repair. How do stem cells find their site? You have this, but basically this SDF1, which I showed in that video, or CXCL12, draws the cells. It is a very specific chemokine. When we look at the stem cell niche, what we used to think about was you had this stem cell and it would differentiate, sometimes make a copy of itself. But what we see actually is that there are various stem cell niches with different stem cell populations. And I really like this slide from Su and Fuchs in 2012, where if you look at this image on the left here, we're looking at the hematopoietic and MSC niche within the bone marrow. You can see that there are two niches. First, the endosteal niche, which is along the osteoblastic lining, and then further in the marrow space where you have sinusoids and vessels, you also have a new sort of niche. Well, the endosteal niche is where the much more immature, long-term hematopoietic stem cells live and thrive. And then as they migrate toward that sinusoid to actually go out through the vasculature for repair, they then become very active and less long-term, right? So what's interesting, though, is if you eliminate macrophages, which you hear, I hear so many clinicians say macrophages are bad. There are two classes of macrophages. There's a class that does bring tissue destruction, but there's also a second class that brings tissue regeneration. So to say macrophages are bad is very, very incorrect. To say white cells are bad is incorrect because it's not accurate. with the data. We have to become better with our terminology. Macrophages can actually support tissue regeneration. And if we eliminate a macrophage, if we eliminate macrophages, it eliminates the expression of genes in those MSCs, whatever you want to call them, that bring these hematopoietic stem cells into the sinusoid to migrate and address the tissue regeneration. So here you can see macrophages obliterated, all these genes are turned off, and we don't get cells migrating. So what's involved? Frequently you see this sort of diagram when it comes to tissue regeneration, and many people refer to it as the Holy Trinity. I am a scientist that doesn't believe in the Trinity, so I've expanded upon this, and I make a diamond rather than a triangle. So cells, signals, scaffold, that's pretty much what everybody says. But what you now know, based on what I've said, is that there are more things that are important. Angiogenesis or vasculogenesis, so having the restoration of the vasculature, and then the physical environment. In fact, if you think about the G1 discussion and where things are stochastic, you can see how important the environment is. With an environment without signals, you have no stochasticity, and you have cells that don't function. So we actually now say the environment is more important than the cell, because we can make cells change their response by just simply changing the environment. Not only the stop of breakdown, but then actually then a turnaround and rebuilding of tissue are found in these biological allografts and cellular therapy tools, right? So we focus on various growth factors and cytokines. This paper, this table I put forth for you for your records comes from a paper I published with Dr. Bob Marks in 2012, and the reason I bring this table in is because it's very easy to read, and we don't go so in-depthly that you lose track of what you're looking at. But in these tables, table 2 and 3, we demonstrate various cells that are found in these biological allografts and what they do, what their role is in tissue regeneration, as well as various growth factors in table 3. So it's pretty simple. Clot master and the clot matrix that gets used really looks at using blood, spinning blood down to get into this buffy coat where we have a separation of plasma and erythrocytes, and it's this buffy coat that has a high platelet count, and these platelets are super critical for recruiting marrow cells. So one method of treatment is with the clot matrix and platelet-rich plasma, and those signals draw cells out of the marrow space through the vasculature. Okay, that's one way of doing it. However, if you have somebody that's got a large defect or has been chronic for quite a long time, most of the time PRP is insufficient because the vasculature is so destroyed to the tissue, it has a hard time recruiting cells into that tissue. So at that point, you then say, rather than relying on automobiles on a highway, which the cell is the automobile and the highway, of course, is the vasculature, we're going to put cells into an airplane, if you will, and inject them into the patient and to that trauma zone. So cells on a highway system might leave Boston, and some will go to LA, but some will go to Sudbury, Massachusetts, some will go to Portland, Maine, some are going to go to Arizona, so they don't all go to just that region of trauma. Versus when we put these cells on the airplane, the injection, the cells get picked up at the airport and they get delivered at the airport, right? You're not losing cells on the flight. You're not losing people on the flight. Otherwise, you have a real travesty. So think about the difference between PRP being sort of a means of relying on the body's vasculature and a biological allograft injection as being an airplane, and you're injecting cells where you want them to be. Now, when we look at, here, I'm going to show you this. When we look at platelets, specifically, the number of platelets has a tremendous play into how well and how efficacious this tool would be. And we know that we need very high platelet counts. We need at least 1 million for this optimal concentration. Okay, now, do we have in vivo results? Yes. As I mentioned, Bob Marks was one of the first users of platelet-rich plasma, and he needed over 1 million platelets per microliter. We know that this study by my colleagues at Harvard looked at two concentrations that were both in the optimal range, 1.2 and 1.9 million platelets per microliter, and found that both were effective. Now what I want to do is demonstrate what happens and what regions of trauma and ischemia are like, and why marrow cells go there natively, and the cells that are found in biologic allograft. If you look at human bone marrow, it has a low oxygen tension. That low oxygen tension drives the expression of something called hypoxia-inducible factor 1. HIF1 then causes an expression of SDF1 or CXCL12, the chemokine that says, hey, stem cells, come here. So you get retention of stem and progenitor cells in the marrow space. And you get some recirculation of these cells through the vasculature, and in homeostasis, we have, say, a tissue that has normal oxygen tension. That means low HIF1, low SDF1, and you don't have these cells just hanging around. However, when we now have ischemia, guess what? It looks like an environment that's similar to bone marrow. Low oxygen tension, high SDF1, lots of stem and progenitor cells assembled, and what do? They build vasculature. Now neovascularization happens, and down here you have a return of oxygen tension, reduced SDF1, and progenitor cells that just sort of flow on through. Now, we did this study in 2010. The first one was published, and there are now 5-year data on heart injection and global ejection fraction, infarct wall movement, and this paracrine effect continues to build and build and build and build. So the paracrine effect is what's driving this. In vitro studies, we know, demonstrated that these hematopoietic cells could do everything an MSC could do. And then we now know that, in fact, the cell that drives tissue regeneration is often an HSC, and that's because following trauma it uses a different line. However, what I need to say very, very clearly and very importantly is that all the data we have shows that having what I call a cornucopia of cells and signals is actually the most effective. So let's not focus on one kind of stem cell. And again, remember, stem cell treatment means stem cells only, and that's an FDA no-no, right? We're looking at biological allograft and cell therapies that are compliant with FDA, and a stem cell therapy is not, and that would be stem cells only. Well, the body, guess what? Favors heterogeneity. We have to have a microenvironment that looks like a microenvironment that the cells know and thrive in, and that requires heterogeneity of cells. And this study by Yasuhara in 2010 demonstrated that extremely clearly, where they broke cell populations down, but it was the group that had the full complement of cells that function best in terms of outcome and tissue regeneration. So we've had a tremendous range of change in thought. We've evolved, so we're not just focused on stem cells only, and we now know that indeed heterogeneity is incredibly important. So the biological allografts are very helpful in demonstrating the importance of the heterogeneity, because those cells found in those biological allografts are heterogeneous. It's not just stem cell. It can include stem cells, it can include progenitor cells, and it will include various types of terminally differentiated cells. And those things are all about stimulating endogenous cells that are quiescent, so basically in that sleep state. So those things, those components of paracrine, juxtacrine, and heterogeneity, those are the biggest things I want you to take home with you for this presentation. And on that, I'm going to stop for questions, because we're at the roughly 10-minute mark here.
Dr. Brimhold, stopping in here, would you tell about the friend of yours that had the biological allografts injected into his elbow as a picture? Tell us the outcome of that.
Sure. You know, I struggle with things like that only because as a scientist I don't like N of 1, right? But we have lots and lots of data on this now. But I will certainly go through this example. So professional pitcher. I know the pitcher and I know the treating physician. The pitcher pitched for the New York Yankees, has the name of Bartolo Colon, right? Was injured to the point where was told his career is over. He messed up his elbow. Bartolo Colon received an injection of cells that from bone marrow, but it's still the same cells that are found in the biologic allograft, or can be. These cells and these signals induced regeneration in that elbow. Bartolo came back pitching harder, faster, and more accurately than he had done in his entire career prior to that time, prior to a career-ending injury, because these treatments induced tissue regeneration. Remember, we get our English word repair from the Greek word for liver, repair. We are doing nothing than what the body does naturally, but we're jump starting it or supplying it with a high enough cell load so it moves out of osis and into repair. So it moves out of destruction into restruction.
Doctor, you may not know it, but we lost sound on you as you explained what a biological allograft was. For 2 slides, we went silent. I don't know what happened. Would you just tell us again briefly what a biological allograft is, and that is what we're doing to get this massive improvement in these areas?
Sure, yeah, absolutely. So a biologic allograft simply says one thing. So there's biologic autograft and biologic allograft. Autograft, the donor and the recipient are the same. Allograft, all it means is that the donor and the recipient are different people, okay? The biologic allograft, what's beautiful about what is marketed here and discussed here is that you have a very clear knowledge of exactly what is in that product. If you did autograft, so now let's say we're going to harvest some bone marrow in a patient, that doesn't ever get studied. It's harvested and it's injected, and it's unclear what was actually injected into the patient. So one of the benefits of biologic allograft is you know what you're injecting. And that's actually pretty important. For me, I struggle with studies that don't actually quantify what's being injected. And there's tremendous variability of products on the market, and many times it can be difficult to determine what's actually in the product, and many of the studies don't necessarily reference or study what's actually in the product, but simply go on purely manufacturer reports, and the manufacturer reports aren't telling you what's in the product, but simply a range that could or could not exist. So in the biologic allograft specifically, you will have you would have in tissue, in that tissue, and in that blood, right? In the blood specifically, you would have stem cells, progenitor cells, terminally differentiated cells, etc. Now, with tissue, it's generally not so much a cell focus, but rather the focus of all the goodies, the cytokines, chemokines, the growth factors that are being expressed by those cells and platelets, which then stimulate those endogenous cells to awaken. So you can actually simply change the microenvironment, and that will stimulate the endogenous cells to activate and do tissue regeneration, or switch toward tissue regeneration and out of destruction. So there are stem cells, there are progenitor cells, terminally differentiated cells, there are white cells, red cells, you name it, cells that we probably haven't even observed or don't have good names for yet. There are a lot of different kinds of cells that exist, but if you're taking that whole tissue, then you have those cells unless they're being washed out for some reason.
Doctor, most of us are not researchers but clinicians, so it's a real treat to get to hear somebody talk about the science at the depth you can do that. I never recommend anything to any patient unless I've gone through it myself, and I've had a series of four different biological allograft injections to reap the benefit from an injured knee, from a fractured back, etc. And I can feel my body regenerating all over. It's pretty incredible. Dr. Harper, who's you and I know and put us together, has literally changed hundreds and hundreds of patients like this pitcher. I mean, he's an over-the-hill pitcher who's done pitching, and he comes back stronger than he's ever been. Now, by a standard thought, that would be impossible unless we have some way of triggering this regenerative process, which I call sometimes the fountain of youth that we've looked for, the Ponce de Leon. And for me, I see this happening. That's why I'm so excited about this, why we're teaching seminars on this, why we're having you as our guest to get the science behind the literally everyday clinical results that we're seeing and getting. Dr. Harris himself has booked like 3 to 4 months in advance, and he can do 1 to 4 patients an hour. I mean, he can do 4 patients an hour, but he schedules other things too because he does our entire 6 steps using the nutrition, etc. And for you now to get out of a wheelchair in 10 years, being struck by lightning, I treat animals that are struck by lightning and they turn to jelly forever. And yet doing this type of thing, an electrical treatment, you were able to regenerate to the point you're now doing competitive, maybe even ridiculously dangerous bike racing. But that had to be
well, my soon-to-be wife might argue that it's sometimes a bit dangerous to do that bike racing. But yes, I do compete at a very, very competitive level. Last week I would have been competing at nationals, only one of the images on that front slide that showed me in a wheelchair happened 3.5 weeks ago, and I was eliminated from being able to race because of concussions, and that knocked me out of nationals, which also then knocked me out of going to Worlds this year. But yes, I am grateful every single day, not only to be riding a bicycle, but to take a step. And that sort of thing is what I want to be able to bring to the world, right? We know that there's a terrible standard of care for patients. And I hope to be part of that change.
Well,
I believe in the regenerative medicine because not only personally, but because the data are there. And the data have been there for 5,000 years. We just tended to look away. And I would say we're making some tremendous strides. And, you know, the difficulty is that we're often making strides faster than our legislators and regulatory bodies can understand and keep up with. So that can lead to some difficulties in the field in terms of misunderstanding. And that's why I really harp on using terms correctly. So if you market biological allograft as stem cell, you are now sort of outside of what is considered safe practice. Because the FDA says, wait, a stem cell therapy is a drug. Well, they say that because a stem cell therapy means stem cells only. So by having heterogeneity, you now eliminate that struggle, right? So we don't have the struggle of it's just stem cell only and therefore a drug. Now, there are other questions, of course, that the regulatory process brings up, but by calling terms correctly, we now can find that they are clinically open to practice.
We're about out of time. Do you see some pressing questions we should address?
I have not seen a single question pop up. I'm on my question screen and there were no questions typed.
I think you were overwhelming. We're just sitting here in awe. And
well, I hope it was fun, at least.
No, it's excellent. The question I'm getting right now, as a chiropractor, been in practice for 47 years, taught the 6 steps to wellness, structure, nutrition, emotional, using the OH nutrition was so advanced, being pre-digested and whole food. Why this all of a sudden? And it isn't all of a sudden, it's just been barely available to people like us all of a sudden, because we have, you're struck by lightning, somebody else has MS, somebody else has Parkinson's. We don't treat the Parkinson's or the MS, but we're seeing people get out of wheelchairs like you and like me and like Doug Grant because we take aggressive steps of things like biological allograft to get the body to regenerate where it couldn't do it on its own. It didn't have enough power to do it. Is that what you're seeing in your research and evaluations?
Absolutely. So, you know, the reason you have non-healing ulcers or non-union of bone or tendinosis develop is because the body's struggling to actually send enough cells to wake up the process of regeneration. So you overcome that by either increasing the signals in that spot dramatically so you draw more cells to it, or you deliver cells directly because the region requires more than just improved signaling. And
that's what we're able to do with this. So just so the people out there, we have our first seminar that we're teaching, Dr. Harris and I, this coming weekend in Phoenix, and it's just flat full. We can't put anybody else in, but we're scheduling one either going to be in California or in the Seattle area. So if you have an office, you want to have it there. We kind of like to have these in offices versus in a hotel. We can do both. So just get a hold of Jason at 480-964-5198, or just go to www.brimhall.com and look at our schedule, see what's going on. And we're not going to let Dr. Harrell get off this easy. We're going to keep bugging him. He and I talk far more often than we can put him on the screen here. But as you can see, a wealth of knowledge. And he and Dr. Harris and Dr. Harper, Dr. Moore will be assisting us in Phoenix next week. And I can't think of anything as exciting out there as what we're seeing unfold here. Can you, Dr. Harrell?
Well, thank you very much for that. And I look forward to more discussion and more involvement. I would say, if people have questions, they can certainly filter through and we can address those as well. But today was difficult in terms of the basic science. I understand that. But if you think about, I was doing this analogy with cycling before the presentation and with weightlifting before the presentation started. If you think about going to the gym and lifting, doing the hard work of lifting, you lift today, you take a break, you lift the day after the break day. it's not the lifting today or the lifting in 2 days that gets you stronger. The stronger comes in the rest period between the lifts. Okay, so that today was a lift day at the gym. Going through all this material was a lot of hard work, but it's going to sink in as you're reflecting in that rest period tomorrow and tonight. It's going to sink in and you're going to expand. You're going to go back to the gym, read more, get more training, but it's those rest periods that is where we grow and strengthen, and I believe that is very true in learning as well. So I think the hour is a good point.
We really appreciate your time and trouble. Thank you who joined us. We're going to sign off now and let Dr. Real get some rest for that rest period of his between workouts. So good night.
There you go. Thank you so much.
Bye-bye.
Bye-bye.